Our next talk is going to be given by Don Ort. Don is a research leader at the USDA ARS Global Change and Photosynthesis Unit. He's also the Robert Emerson Chair, Professor of Plant Biology and Crop Sciences here at the University of Illinois. And also here he's the theme leader for the Genomic Ecology of Global Change theme. So, Don, the title of your talk, Don, is the Improving Photosynthetic Efficiency for Improved Crop Yield. Is this your talk?
It is.
Okay.
Well, thank you very much, it's a pleasure to be here. And so I really wanted to talk about this notion that Steve Long introduced yesterday morning in a bit more detail about the strategy of improving photosynthetic efficiency to improve crop yields. And what I'd like to do is I'd like to explore an ongoing project, and that is this hypothesis or this notion that crops are too green. And so let me begin by giving you a little bit of the rationale that's behind this hypothesis and what the evidence that we have that this in fact may be true, and this may be an avenue through which we can increase photosynthetic efficiency and thereby increase crop yield. And so Steve introduced this relationship to you yesterday about what defines yield potential. And so not to put too much pressure on you of remembering what Steve said yesterday, let me review it, and that is that the total yield that can be gained on agricultural land is constrained by the total amount of visible light that's available to drive photosynthesis. And then that's acted on by 3 genetically determined traits within the plant. And so one of these is the efficiency with which the crop canopy captures the available light. And then the efficiency with which photosynthesis in this crop canopy converts that available light into biomass. And then finally, the efficiency with which the crop is able to convert that above ground biomass into the part of the crop that we find useful. And this is often known as harvest index. And what Steve told you yesterday is that breeding has been tremendously successful at maximizing 2 of these 3 genetic determinants, and one is the efficiency of light capture, and as I'll show you in a minute, many of our best crops now capture about 80% or more of the total radiation that's available during the growing season. And the other thing that breeding and selection have really been very successful at is improving harvest index. And so now we have a situation where in our best crops under the best conditions, as much as 60% of the total above ground biomass is partitioned into the part of the crop that we harvest. And so in the case of maize, that would be the corn grain. But what was also pointed out is that, in fact, the one thing that hasn't been improved very much during selection is this iSEE, this photosynthetic efficiency. And so, in fact, when we look at what the really best photosynthetic efficiency that you get under the best agricultural conditions, it's about a third of what we calculate as being the theoretical. And so we ask the question, what's the reason for that? And so what's the basis for this inefficiency? And a big part of it is explained in this slide. And what this slide is, it just shows the relationship between photosynthesis and the available light. And so, in central Illinois in the summer, maximum light intensities on a clear day are around 1,800 microeinsteins per meter squared per second. What this slide shows is that photosynthesis in a soybean plant saturates at about 20% of that. And so the situation is, if you look at a soybean canopy or even a maize canopy during midday, most of the leaves at the top of that canopy are way over saturation, 5 times over saturation. And so all of this plateau, in terms of they're intercepting light, they're taking in more light, but they're not increasing photosynthesis. And this is unavoidably an inefficiency. And on top of that, what's really important to understand is that, in these dense canopies, at the top of the canopy, photosynthesis is saturated 4 or 5 times. Just 1 leaf layer down, those leaves are light limited. And so we have a situation at the top of the canopy, we're wasting all this light, 1 leaf layer down, we're light limited, and many of these canopies in mid-season have 4, 5, 6, 7 leaf layers. And so when I'm talking about leaf layers, I'm talking about the ratio of the leaf area to the ground area. And this is often called the leaf area index or the LAI, and I'll be referring to that. And so this is just the development of EI, this efficiency of light energy capture across the season. And this is a soybean crop that was grown on our South Farm in 2013. And so what you can see early in the season, day of year 190, and so this is about 15 days after planting. And so the plants have just emerged. They haven't covered very much ground, and so the efficiency of capture is only about 25%. But what you see is by about day 200, when the plants have gotten to the point where they have about 2 to 2.5 times the leaf area than there is the ground area, you're up around 90% saturation, or 90% EI. And so if you integrated that across the season, during the entire growing season, these soybean canopies are capturing, 80% or more of the total available light. But our premise is that, in fact, while EI has been optimized by selection, the distribution of that light within the crop canopy has not been optimized. And by optimizing that, there is the potential opportunity to increase canopy photosynthesis that, again, will lead to increased yield. And so this is kind of just a diagram. And so if you look at our two plants, one is intended to be a full green plant, and another plant, we want to increase the distribution of light within the canopy by lowering the overall chlorophyll concentration. So if you're absorbing too much light at the top of the canopy, why not lower the total chlorophyll that's there and allow more of that light to be transmitted? And so the principle here is that if we look at our full green leaf, at full sunlight, it's way over saturation. And then, as I said, that second leaf layer down, it's already light limited. If we reduce the chlorophyll by 70%, can we go from the situation where now that second leaf layer down is light saturated and the third leaf layer is actually contributing net photosynthesis, allowing more of that light to get deeper in the canopy where it can be used more efficiently? And so this is just a model showing the relationship of what we can expect from the standpoint of manipulating the absorptivity. And so the thing to understand is that as you change absorptivity, two other things have to change. And so absorption, transmission, and reflections all have to add up to 1. So if you're lowering the amount of light that's being absorbed, then more of that light has the opportunity to be transmitted deeper into the canopy, but at the same time, reflectance is also going to go up. And so as reflectance goes up, some of that light is lost. And so at some point, we would project that there's going to be a sweet spot where we've increased transmittance to the point where we're using that light deeper in the canopy more efficiently, but we're also losing light to both to reflection and to transmission all the way through to the ground. And so somewhere there's an optimum. And that optimum probably is going to be below what the current EI is. And so it's very likely that the overall absorption is too high from these canopies in order to maximize photosynthesis. And so this is a simulation that we've done, and I just want to direct your attention to panel D. And this looks at the daily integral of photosynthesis, and so the total amount of photosynthesis that occurs during a day as the sun moves across the sky, as a function of canopy extinction coefficient. And so this is the surrogate for the chlorophyll concentration in these leaves. And so this middle dot here is what the average daily canopy extinction coefficient would be for a soybean crop. And what this model suggests is that if you want to maximize the daily integral of photosynthesis, we should probably reduce that canopy extinction coefficient by as much as half. And so in order to test this, we decided to use some existent light green mutants. And so here at the University of Illinois, we have the National Germplasm Collection for soybean, and within that collection there are about 70 light green mutants. And we screened through those, and one of these is particularly robust in terms of not having a lot of pleiotropic effects and mutation. And this is the so-called Y11 mutation. And so this is in a Clark background, and so we can compare this light green mutant to a full green mutant, and they're isogenic other than the single mutation. And what you can see in the table below is that in this mutant, chlorophyll is reduced by about 80%, and this reduction in chlorophyll reduces the absorptivity of those leaves by about 27%. And so this is a pretty good test of what we want to look at. And so we've used a new instrument that was recently installed in the Institute of Genomic Biology called a light sheet microscope to look at the penetration of light into the leaf. And so, is there a pointer here at all, or not? And so, I just want to direct your attention to these top two panels. This is the full green leaf. This is the light green leaf. And what we do in light sheet microscopy is we can take a laser light sheet from the top of this leaf and then look at chlorophyll fluorescence from the edge of the leaf. And so these are false colored, and this is the wave, or the color of the laser sheet that we're using. So what you can see in the full green leaf is that when we illuminate with blue light from the top of the leaf, that the penetration in the leaf is not very deep. Red light penetrates a bit more deeply, and green light penetrates the best. And so this is exactly what we expect from the absorption spectrum of chlorophyll. Oscillator strength is strongest in the blue, next strongest in the red, and weakest in the green. And that's, of course, why leaves are green, because then more of that light is being reflected. If we go to the light green leaf, what you can see now is more penetration in the blue and more penetration in the red. And so we can quantify this. And so what we're looking at here, let's look at this panel here. And so here we see blue light, and you can see in the light green mutant that this blue light is penetrating much more deeply in the leaf. And so this is the intensity of fluorescence that shows the depth of penetration, and this is the depth from the top of the leaf. Same thing with red light, more deeply penetrating, and not so much with green light because it's already quite penetrant. And so we can turn that into the absorption of visible light, and what that shows you is, again, from the top of the leaf, this is the amount of visible light that's being absorbed, and you can see this big difference between the dark green light leaf and the light green light leaf, and this is the light that's available to be transmitted deeper into the canopy. It's also the light that's available to be partially reflected. And so, in fact, this does result in an increase in photosynthesis in these light green leaves. And so we're looking here at leaf photosynthesis versus absorbed radiation. And what you can see is here is our dark green leaf, here's our light green leaf. And so on an absorbed visible radiation basis, there is more photosynthesis in the light green leaf than there is in the dark green leaf. And so this is what we predict on the leaf area basis. But this, again, is also what we predict on the canopy basis, because more of this light now is available to get deeper in the canopy. And so we did a field experiment with these light green plants, and you can see it here. It's laid out in an N=3 randomized block design, and you can see the light green mutants and the dark green mutants. And we measured lots of stuff, and I'm going to tell you just a few of the highlights. But notice when you look at these light green plants look shorter. In fact, they are shorter. And so we're just looking at the height of the canopy versus the leaf area index. And remember, the leaf area index is that ratio of leaf area to ground area. And so you can see this canopy is shorter, but you can also see that it has a leaf area index that's very similar to the full green. And we think that the reason that it's shorter is that more light is getting into the canopy, and they have shorter internodes. This compares EI between the two, and what you can see is that there is a small penalty for being light green early in the season before you've gotten to that LAI of 2 or 2.5. But overall, the total absorption across the season is only about 5% lower in the light green than it is in the dark green. And so what about photosynthesis? Does this translate into an increase in canopy photosynthesis in the way that we saw that it leads to an increase in leaf photosynthesis? And so this is much more difficult to measure in a reliable way. This is how we attempt to do it with a leaf chamber, an open path gas analyzer inside. The difficulty with these kinds of measurements is you really change the temperature in the microenvironment, and so you have to try to do it quickly. And so what we find is that there is a trend in the light green mutant for higher canopy photosynthesis, but we weren't able to resolve that as being statistically significant. We looked at 4 different growth stages, from an early vegetative stage to later reproductive stages. And this doesn't mean that leaf area photosynthesis has dropped. All this means is that when you go from this vegetative stage before you have a dense canopy to these reproductive stages where you have a dense canopy, this is the inefficiency in terms of oversaturation at the top of the canopy that we're seeing here. Okay. Any ideas? All right, we're okay? For some reason? And so we looked at some photosynthetic characteristics, and I don't want to go very deeply into it, but we did anticipate that because these plants are investing less nitrogen into chlorophyll, that they would have more nitrogen to invest into the carboxylation apparatus, in particular the enzyme ribisco that's the primary carboxylase in C3 plants. And that's shown here by this VC max. And in fact, that didn't happen. And so these plants apparently do not have the genetic intuition to take advantage of that opportunity, and it suggests an opportunity for another kind of intervention that might be put on top of this. And so another thing that's predicted by modeling in terms of a benefit that might be seen from light green is we expect an increase in water use efficiency. And the logic behind this is that if you allow more light to penetrate more deeply in the canopy, you're doing more photosynthesis deeply in the canopy, you're doing it in a situation where the relative humidity is higher. And so the relative humidity is higher in the canopy than it is in the bulk air. And what this means is that there is less of a driving force for water loss. And so these leaves deep in the canopy, if they have enough light, can take up CO2 with less water loss. And so this is just shown here by the latent heat, and so that's the latent heat of evaporation. And what you can see here is for, if we look just here at the average absorptivity, as that goes down, the latent heat of water evaporation goes down, indicating that in fact less water is being used. And water use efficiency can be calculated directly from this. But in fact, that's not what we saw. And so what we saw in this Y11 mutant is actually a lower water use efficiency. And we think that this lower water use efficiency is due to something else we didn't expect, and that is a much higher stomatal conductance. And so stomates are these pores in the leaves that regulate water loss and CO2 uptake. And so when plants are under situations where they have abundant water, they're able to open these stomates, use a lot of water to take up the scarce CO2 out of the atmosphere. However, when they encounter water limitations, as they do most every day, then they close these stomates down and they conserve water. Well, what these Y11 plants are unable to do is they're unable to close those stomates down. And so they have this high unregulated conductance that translates into a lower water use efficiency. And it also translates into these plants being water stressed much more frequently than the wild type. And so we think that this probably explains why in these plants, even though we see higher photosynthesis, we're not seeing higher yield. And so in collaboration with Bob Stuper's group at University of Minnesota, we've localized the mutation in Y11, and it turns out to be in magnesium chelatase. And magnesium chelatase is well known to be a biosynthetic enzyme in chlorophyll synthesis. But more recently, it's also been shown to be involved in ABA signaling. And so It's a receptor for ABA signaling. It's on the outside of the chloroplast. And ABA, abscisic acid, is the so-called drought hormone. And so it's the hormone that's really involved in regulating the stomatal aperture and regulating stomatal conductance. And so we think it's the interference with ABA signaling that's causing these plants to be more drought sensitive. And we think this is the likely explanation that these increases in photosynthesis that we see at intervals during the growing season don't sum up in aggregate to an increase in seed yield and in biomass. And so at the same time that we started these experiments with these light green mutants, we also initiated engineering in order to downregulate chlorophyll synthesis by using RNAi technology on targeted places in the chloroplast biosynthetic pathway. We've done this in a number of different crop plants. And the first of these is out in the field this year, and some of the other varieties will be released next year or be out for field testing next year after we get APHIS permission to do that. And so in these cases, we're going into very specific enzymes in the biosynthetic pathway, and we hope to be able to lower the chlorophyll synthesis, get it lower than what we have been able to do in these mutants, because our theory suggests that we do need to get lower, and we hope to be able to do this without the pleiotropic effects that we've seen in this Y11 mutant. And so I wanted to close with just a few slides and talk about work that's not from my lab, but it's work that Praveen Kumar and Steve Long have led, and they've really asked a different but related question, and that is, do crop plants have too many leaves? And so again, they've taken a modeling approach to guide what they want to do, and what they're looking at is asking the question, what is the ideal LAI in order to maximize yield in soybean? And so a soybean crop at the end of the season will very often have a leaf area index of anywhere from 6 to 8. And so they'll have 6 to 8 times more leaf area than ground area. And what this shows is that this is just modeling what the relationship between this coverage of the ground to leaf area is and total integrated photosynthesis. And what you can see is that there can be a lot of reduction in LAI without affecting total integrated photosynthesis. And this modeling suggests, if we just look at this solid green line, that really, in order to maximize yield, that the LAI needs to be reduced from an average of about 7 to an average of about 4.5, and that this should result in something close to a 10% increase in yield. And so, just like we saw with the light green strategy, by decreasing LAI, there is an increase in a predicted increase in light use efficiency. And so as you go from this normal situation of an LAI of about 7 down to this theoretical area of about 4.5 that would maximize yield, there's an increase in light use efficiency on the order of 10%. And the reason for this increase is pretty much the same as we talked about with light green. It's allowing more of that light to get deeper into the canopy where photosynthesis isn't as oversaturated and can be done more efficiently. And so the way that this experiment was done in the field was, pretty technologically advanced. They sent out a lot of undergraduates with scissors and started clipping off leaves. And so this was done twice during the season, and this can be shown here and here. And soybean plants aren't terribly cooperative, and so when you clip off emergent trifoliates, what they tend to do is they tend to branch and they tend to compensate in lots of different ways. And so there's an experiment being done this summer with even more undergraduates to try to get bigger decreases in LAI. But they were successful again, and so let's just look at the difference between these, I'm trying to figure, so these red and blue circles. And so the blue circles are the full canopy, the red circles are the clipped canopy, And so they have been able to reduce LAI. And even this small reduction in LAI has led to a statistically significant increase in yield of about 8%. And this is very close to what the modeling suggests. And so I've covered two different strategies in which to increase photosynthetic efficiency of the crop that could lead to increased yield, and I think that there's good experimental proof of concept of each. And so this is but one strategy of a way to increase photosynthetic efficiency to increase yield. And this table just lists a lot of the other kinds of strategies that we've been thinking about. And I think what's important to understand is many of these are potentially additive. And so even this reduction in LAI in the low chlorophyll, ought to be synergistic. And so there's lots of other things that can be manipulated. Steve Long talked about some of them yesterday morning in terms of optimizing the investment of nitrogen, in particular limiting steps in chlorophyll synthesis. And so we think that this is a promising way forward, and it's one that we're continuing to pursue. And so let me just end with some acknowledgments. And so most of this light green work that I presented was the thesis work of Becky Slatery, who has recently graduated, and Andy Van Lukey, who is a postdoc and has recently taken a job at Iowa State University, and Kat Grennan, who is a longtime research associate in my group. And all of the lathe clipping work was done by Venkat, who was a graduate student with Praveen and is now a postdoc with Steve Long. So thanks very much.
Time for a few questions. I've got one.
Gene?
When you have lighter green leaves, are there any other trade-offs having to do with insect protection or generation of secondary plant chemistry or anything along those lines?
Yeah, and so of course we don't know all the answers to that, but one very obvious one is that a great benefit of these dense canopies is weed control. And so one of the things that farmers are looking for very quickly is ground cover because it's so effective in weed control. And so I think that this is a potential issue. Another potential one is this whole element of photoprotection. And so these leaves, even the light green ones, are oversaturation to the point where they have very sophisticated mechanisms for photoprotection. And a lot of those mechanisms are tied up with the chlorophyll binding proteins that are associated with these big antennae. And so one of the unknowns is, as we reduce this antenna size, are we going to reduce the photoprotection capacity?
Now, I have two questions for you. The extinction coefficient in plant canopies is a function of the color of the leaves, but also the leaf orientation. Mm-hmm. And soybeans have in their germplasm some varieties that solar track and some that are vertical and horizontal. Has there been any attempt to use that in terms of structuring a canopy that physically facilitates light penetration? Then I want to ask about modularity.
Yeah. And so, not that I'm aware of, and so the tracking that is in soybean is periheliotropic. I think I have that right. Anyway, it tracks the sun, and so that actually makes the situation worse. And so what you'd really like them to do is to avoid the sun for this over. But I'm not aware of anyone that's done that. Certainly, there's been work not in soybean, but in other plants in terms of manipulating canopy structure. And so, maize now has much more upright leaves than it used to, and the same thing is true of the hybrid rices that are so productive.
And so the other question I had is, why does soybean have too many leaves? And my hypothesis is that it was selected for maximum yield, and the leaves are intimately and permanently associated with pod development, because the pods happen in each axis. And so I'm wondering, if you start knocking leaves off, if you start losing those modules that produce the reproductive structures. Now, Steve's data suggests not, because they got to
Yeah.
yield boost.
Well, and so in the experiment that